So I'm here today to give a talk about what I've been working on for my PhD project so far. So I'm also in the group of Professor Giovanni Samai. You heard this talk a couple of days ago. This is all a bit linked to it. I'm also doing Bayesian inference. I'm also doing arbitrary Monte Carlo methods. But all my work is focused on a very specific application, namely mathematical modeling of the human heart. Now, we will not come too close to the biomedical application. Don't worry too much because it might scare some mathematicians away. But I would have to start a bit from the application side. So typically, when somebody is suffering from a heart disease, they're going to come into the hospital. In the hospital, a doctor is going to make some measurements to make a first diagnosis. Now, those measurements are often still made outside the body, very non-informative, very noisy, very sparse. Based on that, they might propose a therapy, for example, an actual surgery, and then of course more detailed information becomes available to steer that surgery at that point. But this entire decision process from data is still far from optimal. To illustrate this, I'll show you a typical case of what a heart disease, or more specifically a heart rhythm disorder, would look like. So you have two images of a heart. The yellow arrows show how the electrical signal is propagating each of them. So what you want is that this happens in a nicely coordinated way, such that this signal activates muscle cells to contract in a coordinated manner as well. Here, you first at the top of the heart that contracts and at the bottom. Now on the image here on the right, you see a very chaotic behavior in the atrium. And because of that, the contraction of this atrium is affected as well. And, well, this type of heart disease is very common, very dangerous. So it's really important to treat them well. How this is done right now is by this type of procedure. Basically, it's going to damage a very small part of your heart, such that it loses all its electrical conducting properties. Because of that, the electrical signal can't pass through that area anymore, and it's going to have to follow another, hopefully more healthy pathway. So you kind of try to break up the chaotic, in this case, for example, electrical behavior by reducing the number of pathways that the signal can still take. What's very challenging in this? Well, while you can categorize some of those heart diseases in big groups, what's actually causing them is very patient-specific. So it's a puzzle that has to be solved by a doctor on a case-by-case basis. As a result, often those procedures can take very long, sometimes they have to be redone, and it's really important that we improve that. So for that reason, people have been proposing cardiac digital twins. So I'm assuming most of you are familiar with a digital twin. In some application, it's exactly the same here. You take some mathematical model that describes your system of interest, in this case a heart, and you integrate all the available data to kind of have one virtual part that contains everything you know about this heart. And then you can use this, for example, to make a prediction on what should be a good strategy for therapy or everything you like, let's say. Problem is right now, this is almost completely deterministic. And the problem of that is that, of course, there's many sources of error in such digital twin. Some are integrated with the data. The model itself is not perfect, so just proposing one prediction based on what's available doesn't tell you the entire picture and can often just be wrong or dangerous. So that's why in our project we propose to introduce a certain quantification to that. So I always have this slide for a bit of an image of what that would look like. Instead of having this one digital twin, you want to have a whole bunch of them. Of course, this would not look as a separate digital twin, this would be some continuous digital twins, but in that case you could use them to make predictions on which also the insert is quantified, which is just more accurate and more reliable. And that brings us a bit to what our general aim was of this project. Using these state-of-the-art models of the heart and those personalized digital twins that have shown their potential, that have been proven to work, but introduce a certain quantification in there to make them somewhat more reliable, so they can actually maybe be used one day in a clinic. So for that I'm working together with a whole lot of people. Here for my name is Giovanni. It's a collaboration also going on between our Department of Computer Science at KU Leuven and the University Hospital. Obviously needed if you work on an application like that. So today I will go through a few things. I will explain a bit the problem setting that we will look at specifically. I will formulate this as a Bayesian inference problem and then explain what type of Maarten Volkaerts we use to solve it. And of course end with some results. So to start with the problem setting, I briefly just remind what I just said. The goal is to quantify uncertainty in such a personal digital twin, but the question is, of course, where do you start? Because there is so much layers of complexity, so many different scales. what type of introductionary case are you going to look at? So what we did is we talked quite a bit with some of the collaborators at hospital, and we ended up on this case. Now, basically, what I can explain what's happening in this figure quite easily, because it might seem a bit daunting, but basically you just see a scan of one of those top rooms of the heart. I've circled, for example, the right one. The colors, they show at what moment in time the electrical signal has arrived at that special spot. So basically, the electrical signal moves along the color gradient, following this arrow that you can also see on the slide. In the middle of that, there's a gray area. This is basically a region where they haven't seen any electrical activity at all. This region has been damaged. So it turns out that in this type of arrhythmia, if your electrical signal ends up propagating around the spiral, you get into something that's not very healthy. You get a very continuous contraction of the top of your heart instead of one coordinated one before the rest of the heart contracts afterwards. So of course you can now model this mathematically. You need a couple of ingredients. So first of all, you can model the atrium with a 2D slab. So of course this is somewhat an approximation, but as you also see on the figure, an atrium is less thick than a ventricle, so it's more common to model them in 2D as well. In that slab you can kind of add a hole in your domain, which would be your non-conducting defected region. And then of course you need some dynamics that model how your electrical signal would propagate through this medium. Those are shown here. So typically this model consists of a main equation, a PDE, a reaction diffusion equation. So the contributions here are on the one hand a diffusion term, which kind of models the propagation, the diffusion of this electrical signal through space. And then you have a reaction term which introduces some effects from a scale lower, let's say, from the cell scale. And this term on its own will depend on some additional states that on their own also follow some ODE equations. So of course, you can imagine that for this reaction term, you can go from very detailed models consisting of something of 20 additional states to something with only one additional state, which would only approximately capture your behavior, but still is of course going to be a lot faster to solve. So for now we went for this type of model. The full description is written in here, so you now have a reaction term with two terms. You introduce quite a lot of extra parameters as well that optimally should be tuned as well. You see several time constants, you see tau in, it's not working very well. Oops. Okay, I'll just pause there.
You can just press the button and keep it, the first one.
Yeah?
Yeah.
Yes, okay. So if tau in, tau out, you have here tau open, tau close, some V gates. Like in theory, you could try to personalize all of them to some data. Last ingredient, of course, that you need an initial condition that somewhat brings your system in the behavior that you would observe in reality. So that's why you see this spiral initial condition here, which in turn would, if you then let your simulation run, give some type of re-entry, quite similar as to what you see here. One main difference, of course, is there you see arrival times, here you see the actual electrical signal. So you have to kind of see that this is the moment at what moment the wave arrived at that spot. And that's basically also the VM in this model. This is kind of your local electrical activity at a certain moment in time and space. For the rest of the slides, I will just always use this formulation of the model, but whenever I say we solve this, I will be referring to the model I just showed you on the previous slide. Okay, so what do we want to actually estimate in this context? Well, there's many things you could do. I've showed you like the reaction term introduces a bunch of parameters, but what we will focus on in the project is mostly the diffusion constant. So this would be, in a disease case, often be a space-dependent function. So you should look at some random fields modeling. But once more, it was an introductory case. So we said, what if we just limit the complexity of this D and just instead consider it as a value that has two values. It has 0 inside the defect and something else outside the defect, and we just try to find this division. So basically we try to find the shape of our defected region. So that brings me to how we're going to make this into a Bayesian inference problem. Of course, this slide has been shown before. Bayesian inference, you won't have some parameter theta that you try to estimate. You can map this parameter to solution of your forward model and then to the observable data with f and h respectively. And on this way you kind of get a result that should be close to your data. But of course there's going to be some discrepancy, and well, you could now model discrepancy parameter and data also stochastically, such that instead of trying to find an optimal fit, you try to find a distribution on your parameter. So posterior on your parameter theta, that kind of takes into account what you've learned from your data y. This posterior follows from using Bayes' rule basically, and in the right hand side you see ingredients like on the one hand the likelihood. The likelihood will for every parameter theta kind of give a score of how likely this parameter would have resulted in your data. Finally, the prior itself, well, this prior you typically will specify yourself and captures anything you know before you actually do your inference experiment. So typically you also see the term in the denominator. This is called the evidence, but this we often don't know. The prior we know because we specify it ourselves. The likelihood follows from your model for your discrepancy in your forward model, but the evidence we don't know. So this is often what we're going to have to get around with more mathematical methods. But before I get to those methods, let's first see how we can formulate this ingredients Bayesian inference from our context, because for now we just said we have a defect we want to estimate. I haven't really given a parametric description we fit in yet. So for this defect, we're going to use an ellipse. We assume the location to be fixed, but of course it wouldn't really change a lot if you also vary this location. And instead we try to find its shape and its angle. So it's basically 2 radii and an inclination angle. We define this parameter theta then as follows, as AB phi with AB radii and phi this angle. Your omega defect, we can also in turn describe this now in function of theta. Of course, this is just a description of how you would describe an ellipse in function of your radii and your angle. To define this forward map that appears in Bayesian inference, we now just have to just do the 2 steps. First, you have to model the non-conducting region. You have to kind of fit this to your theta, and then you have to solve your PDE over the domain without this omega defect. Numerically, this would consist of 2 steps. This first step, modeling this non-conducting region, basically just means find a mesh now that fits your new domain with a shape, with a hole of the form omega defects. Then you can solve your PDE on this mesh. Obviously, it's also going to happen numerically, and well, just for completeness, also includes how we do this. We use a splitting solver, which basically separates your diffusion term and your reaction term. So you take, for every time step delta t, you first take half a time step where you just solve the contribution of the reaction term. Then you use the end value of that as initial condition to solve the diffusion term over an entire time step, and then you do the same thing, but now for the reaction term over the half a time step again. So what you get there is basically you have a value for your Vm at every node of your mesh. And well, every time you solve a reaction term, this will be a spatially decoupled system of ODEs. And then every time you solve the diffusion term, you will couple them in space, and you will solve this with a finite element method. The solution would of course then be an approximation of your Vm at discrete moments in time, also in space somewhat, but of course you could also interpolate that, which is typically done in a lot of finite element method solvers. That brings me now to the last ingredient we need, which is the map between model and data. And this one is also a bit complicated in the sense that the Vm have been modeling. As I said, this is basically your electrical signal inside your heart wall, but there is no device in the world that would measure this directly. You need something that's going to measure something at a distance. It's often going to be an electrical field produced at some distance, produced by this propagating electrical field. So the device you see here is something that typically used in the clinic. What's mostly important is that you have 20 electrodes and they're spaced in 5 arms with 4 electrodes on each, equally spaced from each other. You see that on that figure, but you also see that here in the image how that would look like, where they would be located related to where your medium would be. To actually now map your solution, your local electrical conductivity, to what you would measure by this device, you need to solve this convolution. We have 2 similar forms that are equivalent, at least if you have Neumann boundary conditions, which we do. And well, the second one is somewhat more interesting because you do know the first derivatives when you use first order approximation in FEM. So this is the one we actually use. Now for every location of an electrode, for every RE, you can now, of course, solve this convolution, and you will do this for discrete moments in time, tau-g, because of course the devices don't make continuous measurements but discrete ones, and then you end up with a matrix of time traces. So you have 20 electrodes, so 20 time traces, each of them correspond to one solve this convolution. Of course, once more, this will actually be done numerically with some quadrature formula. Just to show what those data look like, I also added a plot for that, so I will briefly pose it. Here you see a purple dot, so we see what would be measured at this location. And this purple dot here will go over the time trace to say what moment of time we are in right now. So typically those measurements, they will be positive if there is more electrical signal flowing towards them than away from them. Which you see here, for example, you have here it's positive for quite a while because there is this waveform propagating through them. The moment it arrives, it will go negative, of course, because then it's more actively moving away from it than it will actually be moving towards it. And then the data, of course, are generated synthetically, which is just basically saying we take some data through and we solve our forward model and map it to the data. We add some noise. And now we can specify everything we need for a Bayesian inference problem, so we can try to start solving it. So, drink 1 second. So, like I said, we're looking now for this posterior on our parameters theta. We know we can evaluate all the ingredients on the right-hand side, except for your evidence, which is typically then done by using Markov-Chain Monte Carlo methods, who generate samples of this distribution, this posterior distribution. And then those samples, in turn, they could be used as a Monte Carlo estimator of any quantity of interest over the posterior. We've heard a lot about that this week, so we might not have to go into too much detail about that. So what we now contributed to this is we have done 3 things to solve this this Bayesian inference problem with Markov-Chain Monte Carlo, and I will go through them all 3. I'll start with the first one, which is the data dimension reduction. So this data dimension reduction, basically the idea there is that instead of using all the data that we have, the entire matrix of time traces, we want to reduce this to a low-dimensional vector. So this low-dimensional vector is given here by Sy, and it contains 2 types of quantities. T, which is the period of your reentrant wave, the one we showed earlier, and then you have your relative local activation time. So relative local activation time is just you look at all the electrodes, what time it arrives, but you look at this relatively. I've shown for a bit of intuition in what this actually means, I showed this. I added this slide, so basically these are your 20 electrodes. I've written on all of them what time your electric signal would arrive. You could now, this arrival time at each electrode could be your LAT I. You can now calculate the average LAT over all those electrodes. And then for each electrode you can then of course just define the relative one as the difference between the arrival time at that electrode and this mean value. For the period, of course, you then can also just take a look at these average LATs, but you compare subsequent re-entries, subsequent arrivals of your wave. So why would you do that now? Well, one, of course, is somewhat algorithmic driven. You know that if you reduce the dimension of your data, you will, of course, be able to do faster inference. there will be better mixing. The other two are more application driven. One is kind of motivated by what you see here on the right. So basically, instead of finding this eta now, you have to find an eta accent because you need a new noise model that instead of modeling the discrepancy between your time traces now model the discrepancy between those characterizing quantities. And well, finding such model is quite complicated in biomedical applications. We have collaboration going on about that, try to find those. And there's a lot of reason to believe that it's going to be a lot more easy to find a model for this eta accent than it would be for eta. Secondly, and this is also quite interesting if we ever want to use this in a workflow, that now our data are completely independent for time shifts or initial condition. Because if you look quickly back at the previous slide, if I now would just add 20 milliseconds to all of them, all those quantities would remain unchanged. So time shifts, they don't really have any influence. Initial conditions, well, this is a bit based on the idea that as long as you at least arrive in the same steady state, if you compare those steady states with each other, there would not be any difference again. Of course, if you would end up in a different steady state, then yeah, another one. But that's, but at least now for this reentry, you would be able to fit your model to the data. Okay, so we'll just model this for now with a Gaussian. And as I said, this covariance matrix for your eta accent, well, this is kind of a research question on its own. So for now, we just will assume this to be a Gaussian. And with the diagonal structure, of course, you can plug in anything you want later when those results are there, and the methodology wouldn't really change. Then the discretization. So this part I might need to make sure I bring the right messages across. So I'll start with first a very generic statement. So Bayesian inference says that, I've shown this already before, but you have this model for your data, it's equal to your model prediction plus some discrepancy. Now, of course, in reality, you would not solve your model exactly, but numerically, and you would not have an exact observation map, but also some numerical approximation. So and when you do that, you kind of introduce some extra term d, a discrepancy just due to the discretization error. If you ignore this d in your likelihood, the assumption you're basically making is that eta accent is a lot more important than d. You can ignore the d. Otherwise, well, if this assumption would not be valid, well, you kind of underestimated significantly what the discrepancy is between your model and your data. You will underestimate posterior variance and have overconfidence in certain predictions. So this is just a generic statement, because what did we observe? When actually you make this assumption that eta accent is not, when you make this assumption that eta accent is a lot larger than d, but it doesn't hold, you end up with artificial discontinuities in the posterior. So here I'm not showing the posterior but the likelihood, but of course those are just translated into the likelihood. You see a likelihood plot in function of a. Maybe just to recall what a was, a is just your long radius of your ellipse, so we reduce it just to this long radius for now. When you let this vary, then you see that for a discretization of your finest discretization, let's say, and a quite continuous curve, although there is one discontinuity around 9.85 approximately. But if you reduce your spatial discretization, all of a sudden you end up with quite strong discontinuities. And those also in turn end up in your posterior. So the reason for that is that if you look at your discretized forward map, your meshing step will always be discontinuous. If you use some meshing software, it's gonna take any domain theta, it's gonna try to find a mesh that fits it. But then if you propose another domain that's closely looks like it, and you don't tell them anything else, it's just gonna generate a completely new mesh. There is no relation between those two meshes. There is no local continuity. And this is different. And for example, if you now, if for example you would have had the same mesh for every parameter value and you would vary another parameter, very typically those maps will be continuous. And the problem is a bit that if in that case you make this wrong assumption, you probably won't really notice, and you will just go with the assumption that you accurately characterized your likelihood and your posterior, but you've actually made a quite crucial error. And that's quite an interesting property, I would say, of problems like this, that you get those discontinuities whenever you make this error. The real thing, of course, you would be asking is, like, why did you make this error in the first place? So that's quite interesting as well. If, well, once more I brought the model from the beginning. Well, it turns out that those discontinuities also strongly relate to your diffusion term D, the diffusion constant D, more specifically. In this plot, you see the same likelihood as before for a coarse discretization, but now we do this for different values of D. So if D is quite large, you get a quite nice continuous curve. Okay, it's quite zoomed out, so you might still think there are some discontinuities. You can trust me that those are quite continuous. But the more this D decreases, the bigger those discontinuities become. And the reason for that is at least for a big part, related to your observable map. Because now you use an observable map that doesn't necessarily use your VM directly, but kind of derives from your VM at what moment in time your electrical signal has arrived there. So it kind of can amplify certain effects of a discontinuity error, of a discretization error. The most intuitive way to look at this, of course, that if your D decreases, all your arrival times, they will of course increase. So whatever discrepant relative error you make on such an arrival time, in absolute value would increase as well. But your measurement noise, it doesn't change in absolute error. So those two contributions, they become more or less important relative to each other. So when you end up in such situations, of course, when you notice that eta accent, that your measurement noise is not necessarily dominant over your discretization error, there's two things you could do. You could say, let's refine the resolution, or let's model this extra defect. Problem of refining it, there's two for that. One is quite practical, of practical nature, like we were already kind of pushing the limits of feasibility, so decreasing the resolution would have become problematic with just vanilla Markov chain Monte Carlo. Secondly, the idea is also, you also notice that it's quite a hard, if you take this plot into account, it also would make sense that you take a certain discretization, for example, solve an inference problem for a large value of D, and then try to do just the exact same thing for a lower one. You don't always make this correction of saying, oh, you use a different value of D, and that's once more adapt our resolution as well. So by kind of adding this to our workflow, doing like an experiment before our actual inference experiment, where we try to estimate this discrepancy term, we kind of assert certain that we're robust to a change of a parameter that's not very important to your inference experiment in this case. So this extra D, you can of course once more model this as a random variable, introduce it in the likelihood, and then you get with this discretized compressed likelihood, as I call it, compressed because summary statistics or characterizing quantities, discretized because now you also add this discontinuity, this discrepancy due to the discontinuity there. So this idea combines two ideas that are already a bit out there for modeling discretization error in the likelihood. The one is called statistical FEM. Basically, in that approach, you just add two parameters to your already existing Bayesian inference. You add a multiplicative term to your forward model, which typically will kind of correct for some bias. And then you will have your discretization term, which for now you typically only will model with one variance, just one sigma D. So you have two extra parameters, which you then will estimate during Bayesian inference as some hyperparameters. The reason why we didn't follow this exactly is because this mostly works very well if you have a large amount of data available, and we definitely did not because we only had 21 values. Also, this model kind of implicitly assumes that your discretization error would be the same for all your quantities, but since we have two types of quantities, at least you would need one extra for that as well. The other idea which it is based. So yeah, sorry, we finished that. So that's why we just took this extra term D from this type of approach, and we model it a priori, basically. And the way to model this a priori, this is a bit based on what random mesh FEM does. A random mesh FEM will just make any PDE into an SDE, because it's gonna, as a first step, always add a random perturbation to each of your mesh points. So here, your xi are the nodes of a certain mesh you generated with the meshing software. If you just then add a random perturbation, you get a randomly perturbed mesh. In theory, your likelihood then isn't known in closed form anymore, but instead you would have to integrate this over every possible configuration of your mesh. And this is actually just what we do to estimate this sigma d a priori. We will just take one configuration of our domain, we will generate a bunch of different meshes that fit this domain, and by using that we kind of try to model what extra discrepancy is introduced by the discretization error. Okay, then we get to the Metropolis-Hastings algorithm. There, well, I've already shown this also in the beginning of this part of the presentation, but of course we're looking at those sampling methods. And typically, if you sample your posterior at a certain iteration k, you would already have k samples available. And then you will do two steps. First, you will propose a new one based on this last sample. Metropolis-Hastings just does this with a Gaussian proposal. And then we do an accept reject step, basically just deciding that if your posterior, use accept reject, just compares posterior of your proposal with your previous one. So if this posterior value will increase, you will always accept it. If it will decrease, you might still accept it depending on how much it decreases. That's basically what the acceptance probability then counts for. So the two steps we did here is one, the proposal step was adapted such that it can deal with correlated posteriors. So for that, there isn't quite a algorithm already, adaptive Metropolis. But we really need that here because, as it will also show in the results, your parameter theta contains this A and this B value. They both influence somewhat the size of your ellipse. And if you then look at the period of your ellipse, those two will be strongly correlated. So without those, you would quite often get quite bad mixing. And I just illustrate this here. This is what you would get if you just use a typical Metropolis-Hastings. So this is what we would call bad mixing. So every time your A and your B, basically, what you see on the slide is the Markov chain. There's only one Markov chain, but we show the A component and the B component. And what you see here is that the A and the B component, they move in very correlated ways. If the A goes up, the B goes down, and so on. And this you don't really want, because it kind of limits how well you explore your space. If you're in a certain part of space, it's very unlikely going to end up in the complete other part, of your parameter space in a couple of iterations. And this is what causes longer autocorrelation lengths and results in worse estimates. Adaptive Metropolis kind of learns your covariance structure. So basically, instead of just using a Gaussian proposal that doesn't take into account what your actual posterior looks like at all, it tries to still use a Gaussian, but with a covariance that somewhat matches your posterior. And then you get a lot better mixing, because now, as you can see, you can kind of, in a couple of iterations, end up at every point in your parameter space. So your estimates will, the estimates with the same number of times will be a lot better now. Then the second step is about the accept reject step. So I've talked a bit about this impact of discontinuities in your likelihood. But if you look at your actual sampling method, the only place where you evaluate your likelihood is in the accept reject step. In that case, you compare likelihood of proposal with likelihood of your last accepted sample. So those discontinuities, to avoid that they have too much influence on that, you could try to propose some kind of strategy that you kind of can get some local continuity. And the idea, I will first give the idea, then I will show what this would look like in reality. The idea is that for your new proposal theta xn, you generate a new independent mesh, you kind of also give the meshing software your previous mesh as an extra input, which then will be first try to, so the meshing software will first try to shift these nodes so it now fits your new domain. And if the resulting mesh is still of sufficient quality, it will use this mesh. And then you will get local continuity. If, of course, the resulting mesh is of less good quality, you will just go back to the old approach and generate an independent mesh. So this is for now we'll call either independent meshing, which is going to have the subscript EM, or relocating nodes, which is going to have the subscript RN. Okay, so here you can have a nice illustration of what this would look like. So the blue curve is for a rather extreme case, I admit, the type of discontinuities you could see in your likelihoods, for independent meshing at least. So let's say in your Markov chain at some point you're in 9.95 and you would propose 9.97, it's always going to be rejected. And this is solely due to a numerical artifact. And the problems of that are twofold. On one hand, it just completely affects the accuracy of your accept-reject rate, but it also will affect its efficiency, because you will do many of those samples that kind of already could know in advance that they're never going to be accepted anyway. So that's why we propose a relocate node strategy, which basically, if you look again at the 9.95 example, now instead of having a discontinuity a bit further, you kind of get this local continuous extension around 9.95. If you would propose 9.97 now, your acceptance rate will be a lot closer to what the actual acceptance rate for the non-discretized version would have been. You avoid those unnecessary samples, and your acceptance rate would in general be more accurate. Interesting effect of this, of course, is that if somewhat later in your algorithm you end up in another parameter value and you make this local continuity, you can get a completely different likelihood. So for 9.95, you could get all of a sudden a likelihood value that's a lot lower. So you need to take into account that during your algorithm, you might have different approximations to your likelihood. But locally, in the accept-reject itself, it's continuous, and your accept rate should be quite close to what you would want for the exact case. Okay, to show a bit how this works, I added, or show a bit the effect of what this algorithm does. I'll show you a couple of results. So, for now, this is just, for visual illustration, I'm just limiting myself to the parameter, inferring the parameter A. So what we do is we first say like, okay, we're going to solve this on a mesh with discretization, spatial discretization of 0.25. I will call it the finer mesh for now. And we will model this sigma d, this covariance due to the discretization error, based on this discretization. Importantly, maybe to say, your delta t is 0.5, and even more importantly, I reduce my d to quite a small value to kind of increase the effect of your discretization error. Now, if you then solve your inference algorithm with the same discretization, you kind of don't see too much effect of the discontinuities. There is this, you kind of don't see too much effect of your discontinuities. Both give quite similar results. But in this case, you could also kind of expect that, because if your model for discretization error is good enough, this discontinuity shouldn't have too much effect anymore. Now, if you just use the same discretization error, the same covariance for the discretization error, but you coarsen your mesh, all of a sudden you can get very abrupt discontinuities. And these are the most pronounced for independent meshing. For relocating nodes, you still see a hint of them, even more if those discontinuities are closer to the modes of your posterior. But their effect is slightly damped, so your estimate might be somewhat more robust. Moreover, in the bulk of your posterior, your acceptance rate will still be more accurate. So at this point, it's a bit, I will add some illustrations to that. Like as you see, for the same type of for the same step size, you often get a higher acceptance rate if you use node relocation, which are basically mostly few time simulations that you've avoided. But as you see, the mean estimate doesn't really change in neither of those three experiments. And for that reason, I guess the best way to look at it is the following. Well, independent meshing still has one big advantage, that is that whenever you underestimate a discretization error, you kind of get visually warmed, as long as you can see those posteriors visually, because this doesn't really extrapolate well to higher dimensions. But as long as you can, if you can somewhat visualize your histograms, your posteriors, it might pay off to just use independent measurement such that you get this warning. However, if ever you don't, and you just have to hope for the best in some way, a relocating nates might still be somewhat more robust and more efficient, so it might be worth to use it in that case. If you're certain that you estimated your discretization error well, it doesn't really matter that much, but maybe relocating node still has some advantage for one discontinuity that's a bit larger than you would still expect. Okay, that brings me quite close to the end of the talk. I still have some time, but yeah, I'll just add a few results of, well, the complete inference algorithm that I've mentioned in the beginning. So this is for a larger value of your diffusion coefficient, so you don't have to worry about the discretization error too much. You see also the covariance I used for the noise, which is, like I said, for now just an input you choose yourself because we are waiting for information there. And for this type of noise model, you would get pretty decent estimates. However, we also noticed that if we increase, oops, this is a small error there. So actually, the sigma eta xn there is not the noise model I'm using. Instead, I'm using the one that's shown on the slides. Basically, it's a covariance that is wider. You say that there is more noise on your summary statistics, and then you see quite quickly that you start getting some identifiability issues for A and B. Because on these figures now you see in red crosses the samples you obtained, and in the A-B plane they still take quite a big region. So if you would look at A and B individually, you might still have quite a lot of remaining uncertainty. Interesting enough, or not so surprising, you do see that they all lie along isolines of your ellipse parameter, so you do at this point already know your parameter, you do not know the actual individual values. And that's a bit just to see. We're now going to have to see what comes out of the actual noise model and what type of estimate we will get with that. Okay, so that brings me to the last slide. So I guess the main points I want to make today is first of all, uncertainty quantification is essential for cardiac digital twins. We showed an introductory example that now would be used in follow-up work for higher dimensional inference, now not limiting RD to this binary situation, but to more function of space. For now, we somewhat minimized our required number of samples by reducing the dimension of our data and also using those adaptive proposals. And while we use this, we create an algorithm that's also more robust to the discretization error to avoid but it is, of course, at the risk of having overconfidence, so the best thing to do is just make sure you either eliminate any effective discretization error or model it accurately. So thank you. Let me know if there's any questions.